So firstly, we'd like to acknowledge previous work and contributions to this study by Sonny, Martin Scott, John Cowan, Steve Garwin, Bob Brown and Mel Quigley, and to all Peel geologists past and present, in particular Dave Edgecombe for his unrivaled passion, Rob Tyson for his continued backing of the field team, Angus Hornibrook, who despite always looking grumpy is actually a fantastic teacher, and to Mick Oates for enabling the generation of the current model and who really held the team together during a resource drill out that took place during COVID-19. So the Wirlong deposit is located approximately 80 kilometres south-southeast of Cobar and 35 kilometres north of Mallee Bull in the central southern part of the Cobar Basin. It is proximal to the Wurrara Fault, which is a major Cobar Basin structure that runs south to Lake Cargelligo, and the deposit is hosted within the Shum Formation, which is proposed to sit between the informally defined upper and lower amphitheatre group. Copper was initially discovered on the Wirlong Run in November 1900 by legendary prospector John Owen and the co-discoverer Thomas Shuttle. Several pits and small shafts were sunk to exploit the discovery, but the area was subsequently abandoned due to narrow widths of mineralisation. Over a century later, in 2015, Peel Mining drilled 2 holes to test gravity and downhole EM targets beneath a multi-element soil anomaly located 1.5 kilometres north of the historic workings. Both holes intersected high-grade copper-silver mineralisation, marking the discovery at Wirlong. And since then, the deposit has been proven to host an indicated and inferred resource of 4.3 million tonnes at 1.75% copper and 6 grams per tonne silver. The deposit is located at the northern end of a north-south striking, well-exposed lens of the Shuttleton rhyolite member. The lens itself is wholly enclosed within the Shum Formation, with mineralisation hosted at the contact between deep-water turbidites and coherent rhyolite. As previously mentioned, the deposit is proximal to the Wurrara Fault, which is located less than 2 kilometres to the east. Available ages from minimal fossils and correlation with other Cobar Basin units puts the Shum Formation between 412 and 408 million years old, and uranium-lead dating of 2 samples of Shuttleton rhyolite gives it an average age of around 421 million years. So the Shum Formation is represented by the 2 grey units on this cross-section and is a west-dipping, upright westward younging sequence of deep-water turbidites comprising a sandstone-dominant facies and a siltstone-dominant facies. The Shuttleton rhyolite member is represented by the 3 steeply west-dipping orange bodies, and it can be separated into 6 distinct facies, which are as follows: coherent rhyolite, monomic rhyolite breccia, rhyolite sediment breccia, fine-grained coherent rhyolite, flow-banded rhyolite, and volcaniclastic sandstone. And the following section will predominantly describe textures observed in the easternmost body of rhyolite, as the other 2 bodies are poorly drilled in comparison. So the Shum Formation sandstone-dominant facies is the pale grey unit highlighted here. It is dominated by massive fine to medium-grained sandstone that is texturally mature with subangular to sub-rounded grains of quartz, siltstone, chert, and trace detrital feldspar, muscovite, and zircon, classifying it as a sublitharonite. It is commonly interbedded with subordinate very fine-grained sandstone and dark siltstone, and individual beds can range up to more than 10 metres in thickness. Beds are commonly ungraded or very rarely graded in the upper few centimetres. The siltstone-dominant facies forms a relatively narrow screen between the 3 bodies of rhyolite and is formed of intervals of massive or planar laminated siltstone that can range up to 20 metres in thickness. Soft sediment deformation does occur locally within the siltstone-dominant facies, particularly where it is proximal to rhyolite contacts. It includes bedding distortion and truncation and centimetre-scale folds and faults, and is believed to have formed as the rhyolite intruded into wet, unconsolidated sediments. The coherent rhyolite facies forms the core of the rhyolite bodies and is a massive medium to coarse grained coherent rhyolite comprising phenocrysts of quartz and feldspar and minor altered X, hornblende and biotite. Local perlitic, micropoikilytic and spherulitic textures indicates the coherent rhyolite had an originally glassy ground mass. The monomic rhyolite breccia facies occurs along the upper and lower contacts of the rhyolite and is a monomic matrix-supported breccia comprising dark angular class of coherent rhyolite set within a pale, finer-grained rhyolite matrix. It is interpreted as a hyaloclastite that formed by quenched fragmentation of an originally glassy rhyolite as it intruded into wet, unconsolidated sediments. The rhyolite sediment brecciafacies also occurs along the upper and lower rhyolite boundaries and contains a regular class of fine-grained sediment within rhyolite and blocky class of rhyolite within disturbed sediments. The facies is interpreted as a pepperite formed by non-explosive mixing between rhyolite and unconsolidated wet sediments facilitated by quenched fragmentation at the rhyolite margins. The flow-banded rhyolite facies is observed in the core of the rhyolite and is characterized by alternating bands reflecting variable devitrification fabrics that have been subsequently enhanced by domainal alteration. As you can see from the image, the orientation of flow banding can vary greatly over short distances, and the facies reflects intervals of preserved high viscosity within the core of the massive coherent rhyolite. The fine-grained coherent rhyolite facies occurs along the basal contact between rhyolite and the underlying Schum formation, and is compositionally identical to the coherent rhyolite facies, but is much finer grained. And it is thought that this facies represents chilling of the rhyolite margin against the cold, wet underlying sediments. And lastly, the volcaniclastic sandstone facies, as you can see, occurs very locally within the deposit, immediately above the rhyolite. It is massive to diffusely planar laminated and is formed of texturally immature angular fragments of volcanic quartz, minor feldspar, and claser sediment within a rhyolite groundmass. It is postulated to represent reworking of a fragmented rhyolite as it locally breached the Paleo-sea floor. So we believe the Schum formation was likely sourced from uplifted Ordovician turbidites or the unroofed Arimaran granite and deposited in a low-energy deep water setting. The Shuttleton rhyolite was in place as a series of intrusive sills near the basin floor, and this is evidenced by widespread pepperites along its upper and lower contacts. The sills appear to have exploited the contact between the sandstone dominant and siltstone dominant facies within the Schum formation, and quenched fragmentation and soft sediment deformation suggests emplacement of the rhyolite was contemporaneous with sedimentation. So bedding at Werlong predominantly dips moderate to steeply west, but as you can see from the stereonet, is locally overturned to steep easterly dips, and this is due to the folding of sediments adjacent to rhyolite margins. Rare graded bedding, load clasts, and flame structures indicate a broadly upright westward younging sequence. So there are two cleavages present at Werlong. S1 is the dominant cleavage and dips moderate to steeply east-northeast and is interpreted as a regional cleavage that formed during basin inversion. S2 is a steeply west-dipping cleavage and is much less common than S1. It only becomes prevalent at depth in the deposit where proximity to the Woorara fault has caused a rotation of S1 due to drag along the fault. Slicken lines are common at Werlong and are typically formed of quartz and chlorite and less commonly by sulfides. The stereonet shows the poles to plains of the surfaces slicken lines occur on, which dip moderate to steeply east. If we overlay the cleavage stereonet, we can see that this is subparallel to S1. Furthermore, the slicken lines plunge steeply east-northeast, which is parallel to S1, and 87% of all measured slicken lines have a reverse sense of movement. This has led us to conclude that the slicken lines at Werlong formed during reverse dip-slip movement along S1 cleavage planes. Folding primarily occurs in sediments around the margins of the rhyolite and ranges in style from isoclinal to open, like in this example from hole 11. The John Owen Fault is one of three major structures present at Werlong. It strikes west-northwest, east-southeast, dips steeply north-northeast, and is approximately 40 metres wide. Evidence from drill core suggests it has a sinistral shear sense in addition to normal movement. Movement along the fault created zones of dilation that were subsequently exploited by mineralizing fluids. These dilating zones include breccias, veins, fractures, faults, and cleavages. The fault is also easily observed on magnetic imagery, where it runs for over 5 kilometres to the northwest through the historic Cobar-Lyell copper-lead mine. It's also evident at surface as narrow gossanous veins and breccias, and as massive quartz veins that are up to 10 metres thick like this example here. This is caused by dilation along lithological contacts caused by movement along the fault. The Shuttle Fault strikes north-northeast, south-southwest, dips steeply east-southeast, and is a mineralizing fault that forms a conjugate structure to the John Owen Fault. Evidence from drill core, such as these shear band boudins, tentatively suggests the fault had a dextral shear sense. The fault is poorly outcropping, but is observed in drill core as mineralized breccias, fractures, veins, and faults. An example of one of these mineralized faults is provided here from hole 43. So we were able to draw an analogy between the intersection of the plug tank and Cobar faults at CSA and the intersection of the John Owen and Shuttle faults at Worlong. HIND proposes the interaction between the plug tank and Cobar faults created a zone of low stress, drawing in hydrothermal fluids to produce the CSA deposit. We apply a similar model at Worlong, albeit on a much smaller scale, where the interaction between the John Owen and Shuttle faults has produced a zone of low stress, drawing in copper-rich fluids to produce a steeply southeast plunging high-grade shoot. And it is this high-grade shoot that has produced the best intercepts to date, such as 205 metres at 1.4% copper and 3 grams per tonne silver in hole 40, and 82 metres at 2.07% copper and 5 grams per tonne silver in hole 77, which is pictured on this slide. The third and final major structure is the Wurrara Fault, which is a regional scale north-northwest trending fault that dips 55 degrees west beneath the deposit. It has been interpreted as a listric growth fault that was subsequently reactivated as a reverse thrust fault during the Tabaraba and orogeny 390 to 380 million years ago. It is evident in drill core as intense brittle fracturing, cataclastites, and intense silica sericite alteration, like that observed in the example here. And to date, the fault is not known to host any economic mineralization. So for our structural model, we suggest a conjugate fault system that formed during basin inversion under a far-field maximum shortening direction of northeast-southwest. High-resolution topographic imagery supports this hypothesis as it reveals conjugate lineament sets that suggest northeast-southwest shortening. This shortening was accommodated at Worlong by the formation of the conjugate John Owen and Shuttle fault system, reactivation of the Wurrara Fault, folding, and reverse dip-slip movement along cleavage planes. Movement along the John Owen and Shuttle faults created zones of dilation that drew in copper-rich fluids that preferentially flowed into pre-existing structures such as breccias, fractures, veins, faults, and cleavages. As a result, the orientation of copper mineralization is highly variable, which is demonstrated by this stereonet, where the red great circles represents high grade, the blue low grade, and green somewhere in between. This made structural interpretation of mineralization essentially impossible. So with the help of Jung Cowan, we analyzed the locally varying anisotropy, which can be summarized as an ellipsoidal continuity between copper values, which can be simplified to the local planar trend. And if this is making no sense to you, then don't worry, because it made absolutely no sense to me when I first heard it. But what's important is that these values can be plotted on a stereonet, which reveals a conjugate orientation to high-grade copper mineralization. And it is this orientation that near perfectly matches the orientation of the John Owen and Shuttle faults, indicating that the two structures are controlling mineralization at the deposit. So mineralization at Worlong is vein-hosted, and these veins display a variety of different styles and overprinting relationships that can be unraveled to establish a paragenesis for the deposit. The earliest vein set comprised quartz veins that have been deformed and folded parallel to S1 cleavage. The second vein set are extensional quartz veins that exhibit characteristic chlorite and/or carbonate growth fibers perpendicular to the vein margin, and they overprint paragenetically earlier deformed quartz veins, like in this example here. The third recognized vein set are chalcopyrite-bearing veins that are dominated by chalcopyrite with lesser pyrite, pyrrhotite, sphalerite, and galena. These veins exhibit three dominant styles: a composite chlorite sulfide style, which is presented in Figure A, a composite quartz sulfide style presented in Figure B, and a milled breccia style, which is presented in Figure C. These veins overprint and locally offset earlier extensional and deformed quartz veins. High-precision lead-lead dating of galena hosted in these veins has provided an age of 380.2 million years, and petrology strongly suggests that copper is part of the same event. The fourth and final vein set comprises narrow veins of siderite that are commonly vuggy and occur with very fine-grained pyrite. They are the latest vein set and overprint all other vein types, like we can see here in Figure A and Figure B. These veins represent the last gasps of deformation in the deposit, as they appear to offset all other vein types. So this example here from hole 40 does a fantastic job of summarizing the paragenesis at Worlong from one piece of core. Here we have an early deformed quartz vein that has been overprinted by an extensional quartz chlorite vein. Then we have a chalcopyrite bearing vein that partly overprints the deformed quartz vein. And lastly, itself being overprinted by a late narrow siderite vein. Throughout the deposit, sulfides are repeatedly observed occupying sites of low mean stress. Examples of these sites are presented on this slide and include silicon-lined steps, extension along vein margins, extension spurs along vein margins, and the necks of boudinage veins. All of these examples strongly suggest that sulfide deposition occurred syn-deformational, or in other words, during movement along the John Owen and Shuttle fault. Spectral analysis of shortwave infrared measurements has identified the presence of a pervasive background iron-magnesium chloride alteration. It is typically pale green in colour and preferentially alters the ground mass of rhyolite. It is postulated to have formed during hydration of ferromagnesium phenocrysts and the glassy ground mass soon after emplacement of the rhyolite. Silica alteration is typically pale grey, patchy to pervasive, and weak texture retentive to intense texture destructive. It predominantly overprints early iron magnesium chloride in the ground mass of the rhyolite. Ceresite is commonly pale to dark green, patchy to pervasive, and ranges in strength from weak texture retentive to intense texture destructive. High logger data reveals that ceresite has a composition that ranges from muscovite to phengite. Ceresite overprints iron magnesium chloride, however, does not overprint silica, and silica is also not observed to overprint ceresite. In fact, the two often combine to produce a silica ceresite overprint that forms a flanking alteration assemblage around the ore body. And lastly, shortwave infrared analysis has identified an iron-rich chlorite assemblage that is spatially associated with copper, lead, and zinc. It ranges in colour from dark green to black and is commonly localized within faults, fractures, and shears. It is paragenetically the latest alteration assemblage and overprints earlier silica, ceresite, and iron magnesium chloride, like in this example here. So tying together all the evidence, we were able to construct a geological history spanning over 40 million years that begins with the emplacement of the Shuttleton rhyolite and ends with the deposition of siderite veins. So phase 1, deposition of the Shum Formation and emplacement of the Shuttleton rhyolite member 420.8 million years ago. This involved a thick sequence of turbidites that was intruded by crystal-rich rhyolite sills during the Cobar Basin rift phase. This caused extensive soft sediment deformation of the Shum Formation and peperitic margins, quench fragmentation, and iron magnesium chloride alteration of the rhyolite. Phase 2, the onset of basin inversion. This involved the initiation of basin inversion under a far-field maximum shortening direction orientated northeast-southwest. This caused a reactivation of the Ruara Fault, folding of the Worlong stratigraphy, and the deformation of early quartz veins parallel to and during the development of S1. And thrusting along the Ruara Fault caused a rotation of S1 to produce a secondary cleavage, S2. Phase 3, preparation of the Worlong deposit. Ongoing crustal shortening was accommodated through reverse dip-slip movement along cleavage planes and the activation of the conjugate John Owen and Shuttle fault system. Movement along the faults created zones of dilation, drawing in hydrothermal fluids that overprinted early iron magnesium chloride with a silica ceresite assemblage and deposited extensional quartz veins over the early deformed quartz veins. Phase 4, deposition of the Whirlong deposit, 380.2 million years ago. Ongoing dilation along the John Owen and Shuttle faults was exploited by one or more phases of copper-rich hydrothermal fluids. These fluids flowed into pre-existing structures within the faults, such as fractures, breccias, veins, and cleavages, depositing chalcopyrite-bearing veins and overprinting silica and sericite and iron-magnesium chlorite with iron-rich chlorite. And lastly, phase 5, the concluding stages of deformation. This involved the closure of dilation zones within the faults and late-stage movement that is associated with the deposition of siderite veins that overprint and offset all other vein sets. Those are my references, and thanks for listening.